kinematics in 2 or more dimensions. Question for you to think about. A ball is dropped from 1 meter high. At the same time, another ball is fired horizontally at 3 meters per second from 1 meter high. They both depart from 1 meter high. One is just dropped vertically downwards from rest at 1 meter high. One is fired exactly horizontally from 1 meter high, but it's fired at 3 meters per second. Which one hits the ground first? I hope everyone has had a moment to make a decision about which one hits the ground first. I've got some videos for you. The links to the videos are online now. So shoot and drop starting Allen. We've got some equipment that we're taking in. There it is. I guess that's Allen, presumably. And he's setting up this device. It's all level. I guess we can skip forward a little bit. There's the device. So what do? It's got a spring. Okay. So you can put a ball on that end. And when you undo that spring, it'll just drop it straight down, just like in the problem that I gave you. But on that end, it'll fire the ball horizontally. So he sets it up, puts one there, that one will drop, this one will get fired horizontally. And ooh, click, click, click. I'm gonna play that again. Look at this. See which one hits the ground first. Click, click. They are hitting the ground at the exact same time, precisely the same time. That, I think, is very interesting. They hit the ground at the same time. That's surprising to a lot of people, including a lot of you. A lot of you said the opposite, or said that it would be one or the other hitting the ground first. This is a great example. This is a great experiment to show that that's not quite true. Now, let's see if that works with things that are going faster. You know, this ball was going pretty slow. It was not fired off very quickly, but you could do this. So yeah, you can watch those videos on your own time as well if you want. I think they're great. The point of this is that X does not care about Y. Notice that the balls in that first video continue to bounce at the exact same moment as each other. Watch that video again and you'll see that not only is the first bounce at the same time, but the second bounce and the third bounce are at the same moments, despite one kind of staying at the same left and right position and the other one moving off to the right. The velocity that you have in the X direction does not affect what velocity you have in the Y direction. You can have whatever velocity you want in the X direction, and that's not going to change what your velocity or acceleration are in the Y direction. Both of those, in all these cases, both objects, both the one that was just dropped and the one that was fired, they both have the same downward acceleration of negative 9.8 meters per second squared. And we haven't talked about forces yet, but there are no forces pushing left or right on those. And eventually we will see that the force is equal to the mass times the acceleration of an object. So if there's no force in a particular direction, then there's also no acceleration in that direction. And that is good news. As I say here, that is fantastic news to have these things not care about each other. So yes, that's good news. They don't care about each other. The x and the y directions are independent of each other. Therefore, our new equations that we're going to be using from here on out, these are for two-dimensional motion, two-dimensional kinematics, two-dimensional free fall, anything like that in more than one dimension, we will have new equations. Our old equations are over here. V is equal to V naught plus AT. Delta X is equal to V naught T plus 1/2 AT squared. V squared is equal to V naught squared plus 2A delta X. Now we have these brand new equations, but these brand new equations are effectively the exact same as our old equations. Instead of V is equal to V naught plus AT, we have Vx is equal to V naught X plus AX times T. This means that the final velocity in the x direction is equal to the initial velocity in the x direction plus the acceleration in the x direction times the time. Notice that there's no little x beneath the time because there's no difference between time in the x direction and time in the y direction. That'd be incredibly confusing if you had time in two different directions like that. But we don't live in that universe. On the other hand, we do have this equation down here. Instead of Vx, we have Vy, the final velocity in the y direction. Instead of V naught x, we have V naught y, the initial velocity in the y direction. Instead of Ax, we have Ay, the acceleration in the y direction, and we still have T, just as it was before. From here on out, whenever we have two-dimensional problems, you will most likely have to break up the initial conditions or break up the problem into what happens in the x direction using one or more of these equations in the x direction, and also on a different part of your paper have everything going on in the y direction. Effectively, what this means is any two-dimensional problem is actually two problems. You have an x part of the problem and a y part of the problem. It makes it two separate problems, but those two separate problems will probably interact with each other in interesting ways. And we will talk about those interesting ways next time. I will give you these equations, the original ones on that formula sheet. I will not give you these over here, because these on the right are the exact same as those on the left, except those on the right have little subscripts on them. But look, it's x, 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 versus y, 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 y. It's the same equations, just with different subscripts on them. So yeah, I'll give you these, but you don't need me to give you these because you can just add the subscripts in your own brain. And we will get plenty of practice with this so that it's not quite as weird looking. Here's some more stuff. Velocity in x and y. We already talked about how we can take a vector and find the x component of that vector. The x component of a vector is the length of that vector, or the magnitude of that vector, the amount of that vector, times the cosine of the angle between that vector and the positive x-axis. The y component of that vector, the amount it has in y, is going to be the magnitude of that vector times the sine of the angle that that vector makes with the x-axis. Now we can say, oh, my velocity in the x direction is equal to my total velocity, or my speed, if you will, times the cosine of the angle between the direction of my velocity and the positive x-axis. If you do this, this will get you the velocity in the positive x direction. This just says in the positive x direction. Likewise, the velocity in the positive y direction is going to equal the total velocity, or the speed, the magnitude of the velocity, times the sine of the angle that that velocity makes with the x-axis, the positive x-axis. Always measure from the positive x-axis towards the positive y-axis, going counterclockwise around the unit circle. This also works for acceleration vectors. So if we have an acceleration going in some strange direction, then we can break that acceleration up into x and y components of that acceleration. It will eventually work for the magnitudes of things like momentum and force and everything else that we haven't talked about yet. Question for you. I throw a ball at an upwards angle. So I'm not throwing it at the horizon and I'm not throwing it straight up. I'm throwing it diagonally. What is the acceleration of that ball in x and y after it leaves my hand? Assume x is to the right, assume that I'm throwing it to the right, and y is up. Positive y is up. And I give you these options, which use that one vector notation where it's brackets so that the x is the first thing and the y is the second thing. And I was about to say, I will give you a few minutes to, I will give you, say, 30 seconds to look at this and decide what the acceleration will be of an object in x and y. All right, it looks like I'm getting some good answers in chat. Fantastic. The correct answer is D, as in delta. It is 0 acceleration in the x direction and negative 9.8 meters per second squared in the y direction. Once the ball leaves your hand, you are no longer exerting any forces on it. Again, in not too many chapters, we're going to learn about F equals ma. The force on an object is equal to its mass times its acceleration. Once it leaves your hand, I don't have telekinetic powers. I don't think you have telekinetic powers. So once it leaves your hand, you're not exerting a force on it anymore. You're not Magneto, I hope. So when it's left your hand, it should not be accelerating in the x direction because you're not applying a force to it anymore. However, Earth certainly is applying a force to it. Earth is applying gravity, which is a very powerful force, on it. We'll learn about even more powerful forces if we have time. But gravity is going to be trying to accelerate it down at 9.8 meters per second squared, or negative 9.8 meters per second squared in the y direction, because we assume y is straight up, positive y is straight up. Whenever you have a free fall problem, meaning a question where an object is being acted on by gravity, then you can assume that the x acceleration is going to be 0, and the y acceleration is going to be negative 9.8 meters per second squared. If we go back to this slide, that means that in general, if we have a free fall problem, now we're not always going to have free fall problems. Sometimes you might have a rocket, and a rocket can make something go in the x direction. If you fire a rocket off at an angle, yeah, you can definitely get an x acceleration because the rocket is pushing it at a particular angle, which is maybe somewhat y and somewhat x, or you could fire a rocket off completely horizontally and have just x acceleration. That's actually what we had with that stratolaunch problem. So yeah, sometimes we will have an x acceleration, but if we are just in free fall, if we've just thrown some object and there's no rockets or anything weird going on like that, then the x acceleration should be 0. That greatly simplifies these three equations. If acceleration in x is 0, then this last term in each of them just goes to 0. And we see that the final velocity in x is equal to the initial velocity in x. The position in x is equal to the velocity in x times the time. And the final velocity squared in x is equal to the initial velocity squared in x, which is actually just the exact same as this first equation. On the other hand, the y acceleration is not going to be 0 when you're in free fall. You're going to be pulled down by gravity. So this a in these terms on this second part of the right-hand side, those a's are going to be negative 9.8 meters per second squared. Thank you very much. Have a great weekend.